Hello everyone and welcome back. This time I'm gonna show you how we can implement the Runge-Kutta-4th method for integration. This one you can use everywhere where you need to move something, you can use this method. Um, yeah, it's quite easy to adapt to everything. Okay, then let's just add a new method in our code. Below the midpoint code, here I'm gonna say Runge-Kutta-4. I'm just hoping I'm pronounced it right. And here I'm gonna pass again the data time. And then there's something we need to declare. We need to declare 4 variables, and that's gonna be K1, K2, K3, and K4. And I'm gonna add a new function in here. That's something JavaScript specific. You might need to add that method in the rigid body class itself, or if you do the whole integration thing somewhere else, like for example using a strategy software pattern, then maybe in that somewhere, because we need to add a new method which will compute the acceleration for us. I mean, of course, we can do it with plain code, but that's going to be a lot of boilerplate code, and yeah, the function will be quite large. So therefore, I'm going to use a method in the method. This will be a compute acceleration method, and it's going to have the force and the inward mass. And this simply scales or converts the force into the acceleration. Okay, then we're gonna compute K1. So what's K1? What's K2, K3, and K4? If you we can kind of compare that if you use different frequencies, like you have a really a big frequency, then you add a more detailed one, then a even more detailed one, and so on, and you add these frequencies together, then you're gonna have a frequency which has a lot of details. And that's kinda the same with the Runge-Kutta-4. First you're gonna add um, the biggest um, the biggest accurate step, then you add a finer step, and then an even finer step, and then you end up with a quite a good accuracy for the integration. And that's what we're doing here. Unfortunately, we have to calculate every k value first, and here that's going to be the compute k1 first, and that's the acceleration again. Yeah, we're gonna compute that with the acceleration only, and at the end we're gonna combine all these 4 values to get the final delta velocity, and then we're gonna add we're gonna add that delta velocity to the current velocity, and then we can calculate the position out of that and move the shape, of course. Okay, so the acceleration for K1, this is quite easy. We can just compute acceleration with our method here, and we use this dot force accumulator with this dot invert mass. Okay, and then we set K1, we scale the acceleration to get the velocity for K1. Cool. Then the K2. Here I'm gonna say I have a temporary force, and this will be, well, actually, yeah, I'm gonna say temporary force. Yeah, that should work. Here I'm gonna say add this dot first accumulator with the K1. So here scale K1 and 0.5. Okay, and then we get a acceleration out of that. And this will be again compute acceleration on the temporary force with this dot invert mass. And then we can calculate K2, and this will be scale acceleration with the delta time. Okay. Then we have to do the exact same thing for K3. So we can just copy this one, put it in here, say compute K3. We can override the temp force. We need to set here the K2. Acceleration temp force should be good. Then we're gonna say K3 is this one. And also the same thing for K4. K4, this will be K3. This is right. And this will be K4. And then we can combine, well, to get the new velocity. And this is the delta velocity. This is equal to scale. We need to scale something. And here we're gonna add, yeah, that's gonna be a little bit complex. Here I'm gonna say add, another add to K1. Again, a scale, K2 with 2. Then in here we have another add function. We need, again, we're gonna scale K3 with 2. Then in here, in the add function again, K4. And then we're gonna scale everything we added with 1 divided by 6. And that's the delta velocity. And now we can add the velocity, the current velocity, or we can add the delta velocity to the current velocity. This dot velocity with delta velocity. And then we can update or calculate the delta position out of it. And then of course we can move the shape again. So this dot shape dot move with the delta position. All right. All right. What I'm also gonna do is I'm gonna translate this thing here to a more easier representation. And this is well, you know, without the add and the sub. This is the K2 times 2. This is in the braces, I think it's called. And here I'm gonna add plus K1. Should be right. Yep. Then here we have a plus sign again. This is K3 times 2 plus K4 I think this should be right. And this whole thing divided by 6. Or we can also say K1 plus 2K2 plus 2K3, or let's say um, 2K3 plus K4 divided by 6. Okay. Yeah. All right, and this is a more convenient formula what we did by writing this line here. All right, and this is the Runge-Kutta-4th method. I hope that was a little bit understandable. And yeah, see you in the next episode. Bye.